consistency of least square estimator. Let me tell you this. You know, we started working on linear model. A linear model, we have a way to relate the response variable y to independent variable x. And of course, in the model, we actually need to estimate parameters in the linear regression model, which we call the beta naught and the beta 1. Of course, before now, I've walked you through a method for deriving the estimators, the beta naught and the beta 1. And that very method is called the method of the least squared. It is called the method of the least squared because we actually obtain the optimal values of the beta naught and the beta 1, putting into consideration minimizing sum of square error. And that was why it's called method of least squared. Now, when we derive, you know, an estimator, that I'm actually going to show you now, you know, we have a model, a linear regression model. And if you take a look at this guy now, okay, the two of them are called least square estimators. They are called least square estimators. And of course, we derive them, you know, putting into consideration the sum of square error, you know, by minimizing sum of square error. Now, just like every other estimator, you know, if I want to know how valid is an estimator, whether least square estimator or whatever estimator at all, if I want to investigate whether estimator is going to do a great job, then I need to consider the properties of estimator. Okay, you know what we did before. Properties of estimator like unbiasedness, like efficiency, like consistency, sufficiency, and so on like that. I want to tell you the least square estimator is not an exception to this. So whatever estimator at all, we want to know how valid is an estimator. Of course, one of the crucial property is consistency. Before now, I've walked you through what I call, if you take a look at that, the first one that you see is unbiasedness. I've already shown you how expectation of a beta naught cap and a, you know, will be equal to beta naught, and the expectation of a beta 1 cap will be equal to beta 1. Okay, which means the least square estimators are unbiased. I've walked you through this. Now, before I'm going to go into investigating efficiency, consistency, of course, you know, if we want to talk about efficiency, if we want to talk about consistency, then we need the variances of the estimator. And of course, I want to believe the last time we met, we derived the variance of beta naught cap, the variance of beta 1 cap, as well as the covariance of that. But before I'm going to, you know, talk about this, there's something I want to call your attention to. I need you to take a look at this. Let me tell you this. You know, the reason why model is not the same as reality is because a model cannot give us exact representation of reality. And the reason for that is because of the error. If you take a look at that, the error is going to be the difference between, you know, what happened in reality and what model predicts. So if I want to know how good is a model, okay, then I need to be able to investigate assumptions of a model. Let me tell you this. Because our model is not perfect, then assumptions in a model will evolve around the error. I'm going to say that again. Whatever assumptions a model has, it will revolve around the error in a model. What is the error here? Error here is any other factor or a variable that could affect the dependent variable that we don't talk about. And we expect error to behave well. I'm going to say that again. Error can be called disturbances. And we will expect error to behave well. Now, when you take a look at that, error behaving here, expected value of error must be equal to 0. What do I mean by that in practical terms? What I mean on average, effect of other variables that our model don't capture should be negligible. Does that make sense? And that's what we mean by the expected value of error equal to 0. Then what about the variance of error? We expect the variance of error to be sigma squared, because don't forget, depending on the number of observations, if I have 20 observations, I'm also going to have 20 errors. If I have 50 observations, I'm actually going to have 50 errors. Now, errors now become a random variable. What I'm trying to say, the variance of the error should be sigma squared. That is what we call homoscedasticity. You know, we said the error, the error here is homoscedastic. That's a constant variance. And let me tell you this. You're actually going to see in deriving the estimator, we put into consideration minimizing the error. That was why if you take a look at the sum of square error that I'm actually showing here, okay, you know, this guy here is the error that we talk about. That guy is the error that we talk about, because it's the distance between y, actual observation, y, and the predicted model. Okay, now, the other time I actually walk you through, we derive all of this. But you know what? If I want to investigate the consistency based on what you've done before of an estimator, then I need a variance. Or what I'm just going to do, when the sample size, you know, is sufficiently large, I expect the variance to converge to 0. Does that make sense? Why am I talking about variance here? Why is it that I'm not talking about mean square error? Because of this. We're not talking about mean square error because of the fact that our estimators are unbiased. And that's why I want to be focusing on the variances. Okay, now what am I trying to say in the actual sense? Under consistency, okay, there's something I want you to take note. If I have an infinite sequence of data, why do I say infinite? Because I want to talk about consistency. Consistency has to do with a very large, sufficient, you know, sample size. Don't forget, we say n tends to infinity, which means here we expect the bivariate, you know, x1, y1, x2, y2, x3, y3 is going to continue to go to infinity. It means I got, you know, a sufficiently large set of observations. Don't forget, the observation we're going to have is going to be in pairs, right? We're going to have x1, y1, x2, y2, and so like that. Now, it is mathematically proved and statistically observed that when n tends to infinity, the sum of square deviations around independent variable will tend to infinity. Please, I need you to take note of that. You know, this guy, the other time, this guy here, don't forget, you know, we also call it x, x, x. I tell you, remember that? That is the sum of square deviations around the independent variable. Now, in general now, when n tends to infinity, we expect a convergence. You remember what we did before? A convergence in probability will occur between an estimator and the population parameter when n tends to infinity. So The takeaway here is that, okay, you know what? We expect an estimator, beta naught, to convert to beta naught when n is sufficiently large. We also expect the beta 1 cap to convert to beta 1 when n is sufficiently large. But let me tell you this conversion is not going to take place. The only condition under which it's going to take place is when the variance of each of that converges to 0. Okay, because of that, can we now have a way to investigate whether their variances will converges to 0 when the sample size is sufficiently large? Let's talk about, and this is the theorem. Take a look at this. What we're trying to say for consistency, what I'm going to say now, okay, the least square estimators are consistent if and only if our sample size tends to infinity, their variances will converges to 0. Then I need to investigate that. Okay, if I want to investigate that, if you take a look at theorem 9.1, take a look at this guy. You know, the variance of beta 1 is sigma square over SSS. And what did I say the other time? I said, when n tends to infinity, SSS tends to infinity. I said it here. Give me 1 second. Do you see this guy? Right? That is SSS. When n tends to infinity, the sum of square deviation around independent variable tends to infinity as well. It's going to be huge. Now, because of that, take a look at this. When you have a very large number in a denominator, what happened to the whole fraction? The whole fraction converges to 0. Does that make sense? The whole fraction converges to 0. And that is how to show that beta 1 cap is a consistent estimator. What about beta naught cap? Let's take a look at the beta naught cap. We take a look at it, the formula that we derive for the beta naught cap as n as a sample size in the denominator. Not only that, it has SSS. Oh my God, n tends to infinity, infinity times infinity. You know, the whole of that we're also going to converge to 0. This is how to investigate the consistency of least square estimators. Is there anyone who need clarification on this before moving forward? Is there anyone? Okay, I'm going to go to now. We now want to consider simple linear with normal error. Please, I need you to pay attention here. Take a look at this. If I have a simple linear regression model, the probability distribution of the error, okay, is required to be normal for linear regression. Okay, we can also have, and that is the reason why we normally check for assumptions of normality. You know, so when we specify statistical model, we normally specify statistical model with assumptions. And the model can be validated if all assumptions hold. It is not as if our models are failing us, but we are the one that we're not doing the right thing. Some of us are very, very anxious getting results. Like we are too worried. Like we normally rush to getting results. We don't care about investigating whether assumption hold or not. Now, assumption, like I told you, is evolved around the error time. We believe error should follow normal distribution with a mean of 0 and a constant variance of sigma squared. Let me tell you this. It is not only error that should follow normal distribution. But let me tell you this. The moment error in a model follow normal distribution, then the parameters, the estimator will also follow normal distribution. I'm going to say that again. The moment the error the implication of the error following normal distribution that will implies, the estimator is also going to follow normal distribution. Take a look at this. When the error follow normal, then the beta naught cap and the beta 1 cap on their own, they're also going to follow normal distribution. But error need to follow normal distribution first. And if I now want to say that now, because I'm talking about two estimators at a time, I'm actually going to be using vector. Then take a look at this. I'm going to say this guy mean beta naught cap follow normal distribution with the mean of beta naught. Beta 1 cap follow normal distribution with the mean of that. Okay, so this is a vector mean. What you see here? In a situation where you have a vector where you got two variables, you don't talk about variance anymore. But what we talk about? We talk about variance covariance. So this guy here is going to be called variance covariance matrix. Now, the variance covariance matrix, okay, is actually going to look like this. Please, I need you to pay attention. For two estimator, it's going to be 2 by 2, where in the diagonal, I'm actually going to have the variance of the beta naught cap right here. Okay, and here I'm going to have the variance of the beta 1 cap. Okay, we're going to have the variance of the beta 1 cap. Okay, and of course here is going to be covariance. You saw the other time we derived the covariance of beta naught and beta 1. Okay, I'm going to so that's what you're going to put where I put the mark. Let me show you here. That was what we derived right here. Give me 1 second. I'm talking about this guy. Okay, it's going to be a matrix. Now, you now understand what that means now. Okay, and another way we can write the matrix, we can write the matrix to be this row 1, column 1. Okay, this. Okay, we actually gonna have maybe 1 2. Okay, 2 1. Okay, and this is gonna be 2 2. If you take a look at this guy, it's the same thing as the variance of the beta naught cap. This is the variance of the beta 1 cap, and this guy here and this guy here, they're going to be the same. The covariance of beta naught, beta 1 is the same thing as the covariance of beta 1, beta naught. Now, I also want to say this. Apart from using a least square method to obtain the estimator, we can also use the method of maximum likelihood. You remember the other time when I was walking you through the method of estimation, we talk about the method of maximum likelihood and the method of movement. The method of maximum likelihood can be trusted because of the fact that the method of maximum likelihood is based on sufficient statistics. Okay, so we can also have a derivation for beta naught cap and beta 1 cap, the maximum likelihood of that, which I'm still going to show you. And you know what? We can also look at a situation. The least square estimator, is it the same as maximum likelihood estimators? You're gonna see that. But take a look at number 3 here. You know what that guy is talking about? The sample variance is independent of the least square estimators. Is there a connection between the variance, okay, the estimate of the variance, and the least square estimator? What number 3 is telling us is they are independent. And we can also show that they are independent. Okay, but before I show that they are independent, I first want to walk you through, okay, how you can actually derive a maximum likelihood estimators for simple linear regression. Now, I need you to take a look at this. when we want to do the maximum likelihood estimator, we always work with the likelihood function. Now, what is going to be the likelihood function now? We expect the distribution to be normal. Don't forget, when I was stating assumption the other time about the error, we expect that the error should follow normal distribution. Of course, the dependent variable should also follow normal distribution. Okay, normality assumption is required for the dependent variable y and also for error. Does that make sense? Okay, now the underlying distribution is normal. I need you to take a look at this. You know, if you want to write a normal distribution, we normally write y minus mu. Of course, mu is the same thing as expected value of y. And what is the expected value of y equal to? Expected value of y is equal to the module beta naught plus beta 1x. That was why we put beta naught and beta naught plus beta 1x to replace the mean. Does that make sense? Expected value of y in a linear regression is beta naught plus beta 1x. Now, why am I putting this? That's a product, right? Now, this now become a likelihood function of a normal distribution involving linear regression model. Okay. Now, when I have that now, of course, finally, when I simplify the likelihood, I'm actually going to have this. Just like the same way you do the likelihood. The only difference between this and the one you've done before, the one you've done before here is just going to be mu, right? It's just going to be mu. But right now, you are incorporating the model. Okay. Now, when you have that guy, what do we normally do? We actually obtain the log likelihood, right? The logarithm of the likelihood. And when we do the logarithm of the likelihood, I'm actually going to get this guy. Is there anyone who doesn't understand how we go from here to here? You know, going from there to here is to take the logarithm, the natural log. And you know what? You know, when we're using the method of least squared, go ahead. Yeah, that's a good question. So can I explain why we take the log of the likelihood function? Now, this is for mathematical simplicity. Because when I have a function, a likelihood function, okay, maximizing a likelihood function is the same thing as maximizing the log of the likelihood function. But without taking the log, it's going to be complicated. You know, after taking the log, look at what we have. It's going to be easy to differentiate. Does that make sense? I love that question. That's a good question. Okay, now, you know, when we were dealing with when we applied the method of least squared, what are we trying to do? Using the method of least squared, we were minimizing. What are we minimizing? We were minimizing the sum of square error. But using the method of maximum likelihood, we are not minimizing, we are maximizing. Does that mean saying the method of maximum likelihood, that is why it's called method of maximum likelihood. We are maximizing the likelihood. The likelihood of what? The likelihood of parameters. What are the parameters? Beta naught, beta 1. Does that make sense? Now, I needed to pay attention to this guy now. Maximizing the log likelihood with respect to beta naught and beta 1 is equivalent to the minimizing the sum of square error with respect to beta naught, beta 1. Does that make sense? Do you know when that is the same? I'm going to tell you. When the underlying distribution is normal, okay, the two actually going to be the same. So maximizing the log of the likelihood with respect to parameters is equivalent to minimizing the sum of square error with respect to the, so because of that, I'm actually going to say this can proceed in both directions. Take a look at that. Maximizing likelihood is equivalent to minimizing the sum of square error. Any question? You know, statistics is like a story that goes on and on and on. Let me tell you this, if you really want to enjoy statistics, you don't need to miss out on the story. You need to be able to follow the story. Okay, now, when I have the log of the likelihood now, what am I going to do? When I have the log of the likelihood, I'm going to use the principle of optimization, where I'm actually going to differentiate. Okay. For instance, let's say I want to get the variance. You know, there are three things I can get here. There are three things. Please, I need you to focus. Take a look at the log likelihood here. There are three things we can get. We can get beta naught, the maximum likelihood for beta 1, the maximum likelihood for beta naught. We can also get the maximum likelihood for the variance, sigma squares. They are three parameters now. Two parameters for the model and sigma squared. Do you see that? So if I want to do the derivative, I should be ready to do derivative three times. The first one, I will do derivative with respect to beta naught, set it to 0, solve for beta naught. Then I will do the derivative with respect to beta 1, set to 0, solve for beta 1. And lastly, I will do the derivative with respect to sigma squared. Now that's what I'm doing here. Doing the derivative with respect to sigma squared. Okay, I'm going to have that at the end of the day. Okay, I'm actually going to get this. Oh, at the end of the day, and don't forget, your sigma squared, estimate of sigma squared is going to be a function of the beta 1 and the beta naught. Oh, what does that give? Oh my God. This is giving us sum of square error divided by n. You see that? It's giving us sum of square error divided by n. And if I have sum of square error divided by n, you remember when we used a different approach the other time to get the variance, what did we get? It was sum of square error divided by n minus 2. Do you remember? The one we did the other time, using a different approach of obtaining the estimate of the variance. It was sum of square error divided by n minus 2, and we were able to prove that that guy is an unbiased estimate of the variance. But right now, when you obtain your variance by method of maximum likelihood, you're actually going to have a biased result. Okay, so, and that was why I said, so MLE of sigma squared is a biased estimator of sigma squared. But let me tell you this, it is not about biasedness, but the most important thing is efficiency. You could have even though we are anticipating, we're dreaming, the ideal estimator is the one that is unbiased and has a minimum variance. But I want to tell you, in the real world, there's possibility we don't get that. Whether an estimator is biased or not, what matters a lot is what? Efficiency. Does that make sense? So I'm telling you now, I'm confirming to you that that is going to be biased. Now, the next one we want to prove. We want to prove that the estimate of the variance is independent. If I want to prove that the two variables are independent, what do I need to establish? Two variables are independent if what? Their covariance equal to 0. So if I'm able to prove, okay, that the covariance is equal to 0, then it means they are independent. Independent means they are not related. Does that make sense? And that's what I want to do here. Now, when you take a look at the proof, take a look at this guy. You know, we're going to first start by we're considering two random variable. Error. You know, y minus y cap is the error, right? Error and beta 1 cap. Okay, we expect that the error and beta 1 cap should be 0, which means there shouldn't be relationship between the error and what? And the beta 1 cap. Don't forget, the beta 1 cap is the slope. It's the one that talk about the rate of change. In economics, they call that marginal. In economics. Okay, now, when you take a look at this guy now, y minus y cap, right? Okay, now, when you take a look at this is y, a module, right? Y equal to that, right? And this is y cap. Okay, I needed to pay attention. I'll give you 1 second. I'm gonna do something now. Now, this is y. This is y cap. In a y cap, there's nothing like error. Does that make sense? Take a look at that. Comma, beta 1 cap. Now, what is the next thing? That very equation, if you take a look at all of these, I can have a situation where error is going to go with this, error is going to go with a different one, and at the end of the day, I can actually say that I'm actually going to have this, and this. How do I get that? If you use the law of correlation, you actually want to be, combining this guy with this guy one at a time, right? And at the end of the day, this is what you're actually going to get. It's going to lead to 3 covariance. The first one, covariance between error and beta 1 cap. Don't forget, you see the error there, combining with that. There's the other one, the beta 0 cap and the beta 1 cap. Okay. Then the last one, don't forget there is X, right? You see X. Then the covariance of beta 1 and beta 1. Because if you take a look at this, there is a beta 1 here. There is beta 1 here, and there is beta 1 here. So there's possibility. Now, from here now, what is the covariance of beta 1? Go ahead. Why is what? Oh, why is beta 1 and beta 0 without bar? Oh, you mean why is beta 1 and beta 0? Do you say not included? No, they are included. Look at that. Beta 0 cap, beta 1 cap. Oh, the one without cap. Oh, I need someone to tell me. That's a good question. What he's trying to say. You can see in the covariance, the one without cap are missing. Can somebody tell me for extra credit? Why is it that the one without cap are missing? Yeah, exactly. Parameters are unknown but fixed. But an estimator is a random variable. Does that make sense? So if I find it, what is the variance of a constant? 0. So parameters are unknown, but they are constants. But estimator is a random variable. Yes, that's a very good question. Good job for that question. Send me a message for extra credit. Okay, now, when you take a look at this now, I think what I'm going to do today, I'm only going to focus on this material based on my time. Now, take a look at this guy. Covariance between beta 1 cap and beta 1 cap, there should be variance. When I'm talking about within variation, I'm talking about the same variable, right? That is going to be variance. So this guy here is going to be the same as this guy. Does that make sense? Okay, now the next thing we now want to do now is, can we have a way, okay, what is an expression for this? What is an expression for this? What is an expression for this? But if you take a look at this, the second one, we've derived that before. Let me take you back. The second one. I'm going to take you back. The second one. Do you see? We've derived that one before. The covariance of beta 1 cap, beta 1 cap equal to that. Okay. So, which means in the three expression, we've already derived the second one. Okay. We're only going to focus on this guy. Okay. On the first and the last one. And even if you take a look at the last one, we already know the variance of beta 1 cap, right? We've derived the variance of beta 1 cap, which means the only one. So if you take a look at this, give me 1 second. If you take a look at this guy, we've derived it before, is this guy, right? This guy, we've derived it before, is this guy, right? The only one we have not derived now is this guy. Okay, and we want to derive that guy now. Okay, now we want to derive this guy now. And that is what we want to do here. That is what we want to do here. I need you to pay attention. Any question? That's what we want to do here. Now, the covariance of the error and beta 1 cap, we're trying to say, is there a relationship between error and the beta 1 cap? Now, when you take a look at the error here, right? You see the error here, right? Now, the beta 1 cap is this. You remember when we derived the beta 1 cap the other time, it is a ratio of covariance, okay, to the to SSS. So if you take a look at that, okay, that is that. Now, if I have that guy now, I just need to simplify. Okay, now when you take a look at this guy, I can rewrite this guy as this. You remember the other time? Y minus y, but just say y, right? Now, when we rewrite that guy like that, so we are here now. We are here now, right? Now, when we are here now, we want to find the covariance between the error, okay, and that guy now, okay. Now, the covariance between that guy and that guy, let me tell you this, error is also a random variable, okay. Now, when you pay attention, give me 1 second. When you pay attention to this guy now, okay, the covariance here will actually attract y. So it's going to be covariance of y and this guy. If you take a look at this guy, is what you have here, right? Then that guy then is going to give you sigma squared. Okay, so because we have an assumption that the variance of y is sigma squared, so the covariance of the error, because error and y, they should have the same distribution. Error is random, y is random. Okay, then from there, we're actually going to have this guy. Now, the moment you have that guy now, the next thing we're going to do, we are plugging in this, plugging in this, okay, into this. We're going to plug them in. By the time we plug them in, okay, we're actually going to have this. Then when we simplify, that now gives me 0. We know that it's going to be 0 because we don't expect a relationship between the error and the least square estimator for beta 1. So because of that, we now say normally, by normality, we have that error, because y minus y cap is error. Error is independent of the beta 1 cap. Now, if the error is independent of beta 1, don't forget, what we actually want to prove is that estimate of variance is independent of the two, but one of the a way to start is to first justify the fact that there is no relationship between error and the beta 1 cap. Now, the next thing we're going to do now, please, I need you to pay attention. What we now want to do now, okay, we now want to show, we've already showed this. What we have done here is to show the relationship between error and beta 1 cap. We're also going to show relationship between error and beta naught cap. Don't forget, we got two least square estimator. Now, one is just satisfied. Okay, go ahead. Can you say it again? You said, can we assume that because they are independent, we can assume what? Oh, yeah, that's a very good one. That is exactly what we're doing. But we now want to do that two ways. What we actually, I told you from the beginning, I said a model is good if assumptions in the model is met. And assumption is revolve around the error, which means we care about the performance of the error. We want error to behave well. If error behave well, okay, it means assumption hold. Now, what we want to do here is one of the way to prove that error is behaving well is when variance is independent of the other estimator. You remember the other time when we want to derive the maximum likelihood for the variance, what do we do? We do them separately. We differentiated log likelihood function with respect to beta naught. We solve for beta naught. We derive maximum likelihood for beta naught. We do a separate one for beta 1. We do a separate one for variance. Go ahead. Okay, what actually happened is, if you look at what I circle, right? We want to prove that estimate of the variance, that is sample variance, is independent of the least square estimator. What I'm not trying, the way to prove that is you need to first prove that the covariance between the error and beta 1 cap is 0. Then the second one, the covariance between the error and beta naught cap also equal to 0. So when you are able to have those two proofs, then we can make assumption about that the variance is independent of the least square estimator. You know what we did here now? What we did here now is between error and beta 1 cap. What is the next thing to do? Between error and beta naught cap, which is this guy now. Do you see that? Do you see what I want to do now? Between error and the beta naught cap. If you're also able to prove that the covariance between them is 0, then we can now make a conclusion. Now, we're going to do the same now. So take a look at this. Oh, we have it that one again, and and the one without cap disappearing again. When you take a look, where we get just like what we did the other time. Okay, just like what we did the other time. Look at where we have. The other time we were, part of the expression was variance of beta 1, right? But right now it is not like that. So see what we have. Can you see what we have? Can you see what we have now? Right? Now, then it means we need the covariance of error and beta naught cap. Okay? The error here is the one without a cap. That's what we call the error. Let me tell you this. This one here is the error with a cap. What do we call that? Residual. There's a difference between error and residual. Error without a cap is what we call error. The error with a cap is residual. Residual is a difference between y, actual y, and the predicted. Now, if you want to focus on this guy now, take a look at this guy. What happened? Remember, beta naught is what? Beta naught is y bar minus beta 1 cap x bar, right? Now, when you're trying to, this is going to react. So at the end of the day, when you take a look at this, from that, I'm actually going to have this, and I'm going to have this. Error and y bar, error, and those other two. Does that make sense? Now, what is the covariance of error and y bar? The covariance of error and y bar is essentially as the variance of y bar. Why? Error here is a constant. It's not a random variable. But the one that has a cap, so if I have the covariance of those two now, you remember it's just going to be variance of y bar, which is sigma square over n. You remember sigma square over n here? And here, what is this? Okay, this guy is this guy. And the covariance of that is actually that. Okay, we have it in absorption. Now, at the end of the day, we got this guy now. If I now want to go into that, I will now start plugging in that. Okay, so if you take a look at this, okay, we plug in this guy, right? So plugging in that guy is this guy now. Therefore, this, we've derived the variance of beta naught before, which is this guy. Okay, now take a look at this. Of course, we've derived the covariance of beta naught cap, beta 1 cap. By the time you put that, we're actually going to get this. So finally, we simplify. Finally, we simplify. A lot of algebra, sigma square is common to all of them. And by the time you simplify, what you have inside is actually going to be 0. Now, by normality, we now have, okay, the estimate of the error to be independent of beta naught cap. Now, we can now say, finally, since this guy and that guy are all normally distributed, so since, this is the first one we prove, right? This independent of that, this independent of that, then we can prove that the difference of that is actually, take a look at this. We can say that this is actually independent of that. And if I want to get the variance, if I want to get the estimate of the variance, I will actually go through the sum of square error, right? And what is the error? Y minus y cap. So if you take a look at this now, that is the implication of that. Without all this, there's no way we can validate approach in that we use in applied statistics. Okay, so this is going to be the end of my lecture today. Is there anyone who want to ask question or who need a clarification before I go today? Is there anyone? Okay. So make sure you all stay safe and have a lovely day.